multipath. There's reflections from everywhere, and this really is not, you might think there's a problem, that actually in some cases help you. As you can see, if we move farther out, approximately 6 meters, it actually, we're above the predicted transmission increase. And so the point of this is that there is multipath everywhere. But in a typical environment, you can expect that there would be about 100 microwatts of available power at 6 meters and about 10 microwatts of available power at 20 meters. So the question is, of course, how do we take this available power and convert that to DC? And that's where the voltage multiplying circuit comes into play that we've kind of discussed about, but it's just a diode and capacitance change. So we built two different prototypes, a single stage and a 4-stage device based on the Avegotech HMS 285 series diodes. And you can see that our models do predict what our measured values are getting. And you can also see that the output voltage greatly depends, of course, on your load. So this is more clearly shown on this graph, that as there are two different loads, 85 kiloohm load and a 200 kiloohm load. As the number of stages in your voltage rectification circuit changes, your efficiency greatly changes. For instance, you can see on the right graph, there's a 12-stage device. Great number of stages that has a very high energy efficiency. However, that's at a very high power, and with a passive RFD, we're low power. So we want to be able to maximize the efficiency and output voltage that we get at low power. Since we're using the MSP 430, this turns on at 1.8 volts. So we'd like to be able to maximize our power transfer at 1.8 volts so that we can operate the furthest distance possible. So really our efficiency is a function of the number of stages and our load impedance. This plot is showing, this is something to show that if you know your load, you can then, once you characterize your load, you can get the optimal number of stages so that you can have that power efficiency at 1.8 volts. So right now we're using a 4-stage device because our actuation software is near to 200 kiloohm. But as we add more processing, that'll drop down, and 4-stage will be our best choice. The other thing I want to talk about is the communication channel. Typical RFID tags use amplitude shift keying or phase shift keying. They modulate between the conjugate, or they modulate between being matched to the load or shorted. We want to bring passive QAM modulation to RFID and the WISP. We're doing that by modulating between 4 distinct impedance states. And that way we can modulate the I channel, or the amplitude, and the Q channel, the quadrature, simultaneously. What this does is that we now can broadcast 2 simultaneous streams of data. We effectively double our bandwidth for a constant bit period. And we're doing this by integrating RF switches with our matching networks. We can short the shunt components. So we've done this in simulation. This is an Agilent ADS model, and this is an outcome. You can see the 4 distinct groupings, but we're doing this just by having the 4 distinct impedances, and we've been looking at that through a coupling link and looking at an IQ demodulated.
The last thing I'd like to talk about is something that's very new. We did, as I mentioned before, tape out a RFIC that implements most of the WISP RF hardware. We use the AMI half-micron process, which is very inexpensive. It's very bad if you want to integrate a lot of logic in that process. It's a high-voltage process that has a threshold of just under 3 volts. But from the point of view of implementing diodes and simple switching elements, actually those transistors work pretty well. And the diodes and transistors are comparable in size to what you would see in the Agilent or Avego components. So if you stick to the RF, the half-micron process is actually pretty nice. At this point, we have integrated the matching, power harvesting, voltage regulator, and modulation components. And then the only thing that would be remaining is the microcontroller. And we wanted to stay out of that business because implementing logic or implementing a micro is something that we would leave to Intel or to TI, and just try to simplify the overall hardware as much as possible. I'm sorry, that's an error. There is demodulation in there. Yeah, I think the WISP RFIC is I moved that around. So you can see in the dye micrograph here, this is about 1.5 millimeters on the side, and we have 2 independent channels of harvesting. One is done with Schottkys, and one is done with FET connect or diode connected FETs. and then we have 100 picofarads of storage capacitance on each of those nodes. So we have a little bit of RF bypass and storage on the die. That's kind of, as you can see, consuming a lot of the area, so that's kind of the limit of what we can pack onto the die. We would still need an external bypass capacitor. So at this point, we have done sort of an initial functionality check on this die. We got it back at the end of August, and we've done testing with the probe station, and we're about to wire bond them onto chip on board to actually build WISPs out of them. With that, any questions?
So any questions? Raise your hand. I'll bring you the mic so that we get it.
Do you know whether the Schottkys or the diode-connected transistors perform better?
According to the simulation, they perform better in different regimes. So the diode-connected FETs perform better under a different set of matching conditions than the Schottkys do. In general, the Schottkys have a much higher efficiency at low input power, but they have a relatively high equivalent series resistance, so they supply less current at high input powers. So there is a trade-off there. And one thing we can talk about later, actually offline, is about your comment about trying to build a Maxwell's beam, and I think there's a much easier way to do that involving biasing the harvester.
UW is going to talk about their SOCO WISP. Am I saying that correctly?
We've heard, oops, sorry about that. SOC WISP, SOC WISP, or SOCO WISP. They all work. All right, it's a little bit on the loud side. Hello, everybody. Okay, so we're going to, this talk is we're coming at this from the point of view of a wireless sensor network. A little up. Okay. From a wireless sensor network perspective. And so our motivation and what we've been working on for a number of years now are very tiny wireless sensors. And we're not too wed to any particular technology. This could be using energy harvesting, wireless power transfer, et cetera. We just want to figure out what the right tool is for the job. And as we've seen so far, there are a lot of different jobs to do in terms of automotive sensing. Biomedical monitoring is one that we're going to hear a lot about today. Environmental monitoring, etc. An observation we've made, and this is coming out of, the active tag, wireless sensor network community, is that the radio burns a lot of power. And this is one thing that brought us towards the WISP community in the first place, is that we can really change the way that we're communicating with these tags. The other problem is that the size of the radio components is big. So for a variety of reasons, we were really tired of big active radios that were used on wireless sensor nodes. Okay. So the question is, that's fine, but is Moore's Law going to help us? Is it going to make wireless sensor nodes disappear? And so the question is Moore's Law enough? So a couple of years ago, we tried taking sort of the best off-the-shelf components we could and build up a sensor node to see how small we could get it, to see how low the power could be. And there have been a few other efforts in the community as well, people trying to make low-power sensor nodes. So as you can see, the size is quite small. Even compared to WISP, the sensor node looks pretty small. The problem is you also need the antenna, like the WISP, but you need the battery, and that's the hard part. It shares a lot of the same hardware, MSP430 microcontroller, but of course, instead of a rectifier, we have a radio. So there's big problems in terms of power. And you can duty cycle as much as you want, but the peak power for receive and for transmit, even at very low transmitted power levels, is very high, on the order of 30 milliwatts or 20 milliwatts or so. That makes it such that we cannot power this node from, say, a really tiny hearing aid battery or a watch battery. So that's a problem. There's a time problem as well, trying to get the frequency synthesizer and the radio to lock. So you have a lot of complex circuitry on chip to get the radio to work. Getting that lock time, especially if we're in a communications paradigm where we have very short packet structure, gives us a lot of power overhead. There's a fundamental problem in terms of the size as well. If we would like to shrink down these tags to something that could go onto, a dragonfly or a moth or even a contact lens, we can't use the typical approach where you have surface mount components that are plastered onto a PCB. Other components that we take for granted, like the quartz resonator for the radio, is no longer feasible. So there's a huge problem. in the way that these systems are typically done.